Warrior 1 and Warrior 2 are just two noteworthy examples that highlight the incredible significance of space probes in expanding our understanding of the universe. These remarkable spacecraft serve as our eyes and ears, providing us with invaluable real-time information about our solar system. This is especially crucial when direct study is not feasible, as many phenomena in space can take years, if not decades, to fully comprehend. Recently, however, the strange data that Voyager 1 has been sending back from the vastness of deep space has raised intriguing questions among NASA engineers regarding the possibility of unusual messages or phenomena. Should we be concerned about the implications of this data? To understand this better, let us delve into how Voyager 1 has been influenced by an unknown force lurking in the depths of space. For nearly 45 years, the Voyager missions have played a pivotal and groundbreaking role in space research, providing some of the first and most consequential observations of our solar system. NASA's twin Voyager spacecraft, Voyager 1 and Voyager 2, are nothing less than true time capsules from their generation. These vessels were equipped with an 8-track tape recorder designed to store data, but with a capacity billions of times smaller than that of today's most basic mobile phones. To put this into perspective, while modern technology allows us to communicate with lightning speed, the Voyagers transmit information at a rate that is up to 38,000 times slower than a contemporary internet connection. Despite these limitations, these pioneering operations have continued to sail beyond the solar system, bravely traversing the vast galactic ocean known as space, territory where no other probe has ventured before. These missions are providing a unique and unprecedented picture of the interactions between the heliosphere, a bubble created by the Sun, and the interstellar space that surrounds it. Scientists are diligently comparing data from the probe's first emissions with more recent observations, as the extensive history of the Voyager missions offers an unparalleled opportunity to analyze changes over time. No other spacecraft has so profoundly transformed our understanding of the Sun and its impact on the space environment like the Voyager missions have done. Each spacecraft, besides its scientific contributions, also acts as an ambassador for humanity. They carry gold records featuring an eclectic collection of musical recordings, greetings in numerous languages, images depicting the diversity of life on Earth, and diagrams of basic scientific principles, all intended for whoever might encounter these probes in the distant future. The gold coating on these records acts as a cosmic message in a bottle, as its remarkable resistance to corrosion in the harsh conditions of space ensures that the information they contain will remain intact for more than 1 billion years. As scientists continue to analyze the data sent back by the Voyagers, they have been surprised by the strength and direction of the interstellar magnetic field, which has sparked intense debates regarding the shape and behavior of the heliosphere, the magnetic region dominated by the Sun. The heliosphere was long thought to be comet-shaped, trailing behind the Sun as it moves through space. However, recent findings suggest that it may be more spherical than previously assumed. One significant question that arises is whether the heliosphere expands and contracts in response to the appearance and disappearance of sunspots, or whether it maintains a relatively constant shape. The spacecraft have provided intriguing clues to this question, but the debate among astronomers continues. Astronomers suggest that the interstellar medium, the matter that exists in the vast spaces between stars, begins when the solar wind, a continuous stream of charged particles emitted by the Sun, dries up. This plasma, or ionized gas, interacts with a cooler, denser interstellar plasma. Much like a stone thrown into a stream creates ripples. Similar to the way Earth's troposphere has a boundary layer known as the tropopause, the heliosphere has its own boundary called the heliopause, which is distinctly shaped by the Sun. The exact distance of the heliopause was a mystery at the time Voyager was launched. Although Jupiter is only 5 times the distance between Earth and the Sun, some scientists speculated that the heliopause might be relatively close by. However, as the spacecraft traveled farther and farther away from the Sun, estimates of this distance increased significantly. It was at the points near Jupiter, Saturn, Uranus, or Neptune that Voyager's entry into interstellar space was finally marked. The probe detected signals from the heliopause shortly after its encounter with Neptune in July 1992. This marked a monumental milestone in our exploration of space. Both probes began recording powerful radio signals at frequencies of about 2 to 3 kHz. Some scientists theorize that these radio waves might be related to 6 large solar flares that occurred more than a year before they were detected. Plasma ejected during these solar flares reached the heliopause, causing electrons to vibrate and emit radio waves. Although these signals were too weak to be detected on Earth, the interstellar medium is notably much denser than the outer regions of the heliosphere. The distance to the heliopause was determined by measuring the speed of solar material and the time it took to reach that boundary, a distance that varies between 116 and 177 astronomical units. On August 25, 2012, at a distance of 121.6 astronomical units, Voyager 1 made history by crossing the heliopause. There were clear signs indicating that it had crossed this significant boundary, such as the disappearance of high-energy particles from the solar wind, suggesting that the rest of the solar wind had also been left behind. In addition, cosmic rays from outer space, which are partially blocked by the heliosphere, increased significantly after Voyager crossed this boundary. However, not all scientists were immediately convinced by these findings. At that time, Voyager 1's plasma instrument had stopped functioning, which prevented it from recording the dramatic increase in particle density that typically occurs when leaving the heliosphere and entering interstellar space. Furthermore, the magnetic field beyond the heliosphere was expected to have a different direction than what was observed, but that did not happen. The similarity in the orientation of the magnetic fields, both inside and outside the heliosphere, remains a perplexing issue without a clear explanation. The Sun also plays a critical role in these discoveries. In early 2012, solar storms began to occur with increased frequency. In the following year, these disturbances significantly shook the plasma that Voyager 1 was passing through. As a result, electrons in the plasma began to oscillate, generating radio waves that the spacecraft could detect. These waves indicated that Voyager had entered a much denser region of space. In 2018, Voyager 2 also crossed the heliopause on November 5. This time, there was no doubt about the probe's findings. Its plasma instrument was functioning correctly and successfully recorded the increase in the density of various particles, including protons, electrons, and other charged particles. It also measured the temperature of this region, which ranged from an astonishing 30,000 to 50,000 Kelvin, significantly higher than that of the interstellar medium. It is likely that the plasma was compressed as it entered the heliosphere, explaining the observed phenomena. As in the case of Voyager 1, the probe observed a notable decrease in the solar wind and an increase in cosmic rays originating from outside the solar system. However, the magnetic field did not change direction, confirming that the results observed 6 years earlier were not an anomaly. The relatively close distance suggests that the heliopause is indeed stronger than previously thought. Both Voyager 1 and 2 probes are still moving away from the heliosphere, the precise shape of which continues to be an enigma. Since the signals they send travel at the speed of light, it takes more than 22 hours for their data to reach Earth. By the end of 2023, when Pioneer 10 finally ceases operations, Voyager 2 will have traveled a remarkable 129 astronomical units, marking it as the second farthest spacecraft ever launched from Earth. Both probes are traveling in opposite directions, venturing farther from our planet than any other human-made object. Scientists have reported that Voyager 1 detected a hump related to waves in localized regions of the early empty space between stars. As the probe's plutonium power source degrades and generates less heat, NASA has reported that to compensate, the team has disabled several systems, including some initially considered essential, such as the heaters that protect instruments from the frigid cold of space. Remarkably, all 5 devices whose heaters were turned off in 2019 continue to operate without issue. The Voyager's remarkable longevity at much lower temperatures than anticipated remains an enduring mystery to NASA scientists. In 2022, Voyager's attitude control and articulation system experienced a failure, a critical system that is essential for keeping the antennas accurately pointed toward Earth. Prior to this failure, the probe's performance had been flawless, but soon after, the craft began sending incorrect telemetry data due to a malfunction in an onboard computer that had ceased functioning years earlier. This confusion disrupted the craft's ability to determine its orientation in space. However, NASA engineers managed to tackle the problem by having the system revert to using an older computer that was still functional. Despite this technological success, Some are beginning to wonder if the time has finally come to consider retiring the Voyagers, the oldest and most distant spacecraft ever launched by humanity. Although the mission remains viable and continues to yield valuable scientific data, several scientists are already exploring the possibility of developing successors to the Voyagers, pondering what new technologies could enhance our exploration of the cosmos. No one can say for sure how long these remarkable probes, which rely on plutonium to generate heat and keep the fuel that aligns the antennas toward Earth from freezing, will continue to operate. Over time, plutonium degrades, producing less power each year. As we reflect on the extraordinary journeys of these spacefaring vessels, let me know what you think in the comments box. If you enjoyed the video, don't forget to give it a like and subscribe. Then, I look forward to seeing you in the next video as we continue to explore the mysteries of space together.